Hello everyone, and welcome to Scientific Methods 2. In this discussion, I am going to show you how we can use our computer and a particular program called Graphical Analysis to make our graphs and do our lines of best fit and figure out slopes and Y-intercepts and basically everything we need to know about a graph to turn a graph into a math model. So here's the example I used in Scientific Methods 1. Peter Popper plants prodigious plots of pea plants. And here's the data that he measured. Every week he took a measurement, and these were the different heights. So now I'm going to open a program called Graphical Analysis and show you how to use it. This program's kind of nice because it's free, and you can download versions of it to run on just about anything. Right? You can run this off of your phone, off an iPad, off a laptop, off a desktop. Right? And again, the best part perhaps is it's free. Right? So we're going to be using this a lot. And not only does it actually graph, it actually runs some of our equipment that we have. Right? We're going to use it for that too. But for now, I'm going to show you how to graph. So let me open it up. There we go. And here's the opening screen. Now I'm going to make this big for now. Okay? There's a few choices here. Right? We are going to later, when we're running equipment, use this sensor data collection. But for us, all we need is manual entry, because that's what we're going to do. We're going to type some data in and look at the graph. Now, by the way, everything that I show you here is going to be on a sheet that you have access to called Data Analysis with Graphical Analysis. So you see that when we click on manual entry, we end up with a big old graph and a data table. But it looks pretty generic. Right? All it's got is X and Y, right? It looks kind of like a math class. And as I've said before, this is not a math class, this is a physics class. So we're going to change some things so that we can format it nicely and see what we're actually doing. You'll notice that one of the nice things about the program is there's really only a few buttons. There's one down here, a couple over at the bottom left, a couple over here, and a couple other little sideways snowmen that we can click on around here. So there's not a lot of places to click to do things. Okay? If we want to change something about the column headings, we're going to click on the little sideways snowmen here on the column headings. You'll notice that if you hover over it, it says Column Options. So we click on it, and we're going to choose Column Options. Now, it gives us a place to type a name. Well, if you remember from our previous discussion, our horizontal axis is our independent variable. And in this case, our independent variable is the time. And it also gives us a place to type the units. We might use an abbreviation, or in this case, weeks is pretty short, so we might just type in weeks. Also gives us a place to choose how many decimal places or significant figures we use. More about that later after we know what significant figures are. We hit apply and watch what happens. It's changed the column heading. And not only has it changed the column heading, it's changed the label of the horizontal axis. It's smart, right? It knows they're connected. We can do the same thing for the vertical axis. Sideways snowman, column options. In this case, we have height. And we measured the height in centimeters. Rather than writing out the word centimeters, lowercase cm for centimeters, and apply. And now we have height and time. So it's already here changed the column headings. It's already changed the axes labels, all in kind of one thing. So next thing we might want to do is add in our data. This is basically just like you would in anything, any kind of table. You can type using the number pad, or the thing above the letters. Really anywhere. You can use the arrow keys to move around and that kind of thing. So I'm just going to type in the data that we had. So there's the data. And did you notice what happened? Every time I typed in a point, it automatically graphed it. And it even auto-scaled the screen. Do you see how the last point is all the way up here in the corner? Right? So it didn't leave all the data smushed down here just because of how it set up a default scaling, right, it automatically kind of auto-scaled it for us. There's other ways of doing that. Sometimes you just double-click on it and it automatically auto-scales, or you click somewhere, right? Notice if I click on the graph, it gives me an examine button that I can move around. So I can see the points, right? Tells me the data. 2 weeks, 22.4 centimeters, right? 24.7 or 4 centimeters, 2 weeks, right? So that's kind of cool, right? So what now? Well, now we've got the data there. Let's say we want to add a title, right? We'd like to have titles so we know what we're graphing. Well, there's a button down here in the lower left corner, which is called Graph Tools. If you click on that, it gives you a bunch of things you can do. Right? One of them is Edit Graph Options. Click on that. Well, here's a little box that says Add a Title. We always go dependent versus independent, height versus time. There's other things we can change in here. We can change whether there's points shown, whether there's lines drawn between the points, or whether there's points and lines. See that changing on the graph? In this case, I just want to use points. There will be cases when it will help to see both, because that way you can kind of see a pattern, but I'm going to just leave the points on. We can also change the scaling. Okay? Let's say, for example, I wanted to have a 0, 0 in there. All right? Maybe my data didn't have a 0, 0, but I want that to be on my graph. Well, our data has a 0, 0, so I don't really need to do this, but I could click Always Show 0, and that would change the scaling so that 0 appeared. And I could do the same thing down here for the y-axis. That's sometimes handy. All right? Auto-scaling from 0 is what that's called. But right now I just want to put a title on, and there it is, and there's my title. See how we can do all the pretty formatting things pretty easy? And again, you'll have a sheet that has all the steps to do this, right, that you can look at anytime you're trying to do this yourselves. So now let's look at the pattern. Does this look like some sort of pattern? I think it does. Right? I would say it looks like a straight line. So what we would need to do now is what we talked about doing, and we did by hand with our Circle Lab data, which is we need to draw a line of best fit. We need to do the statistical analysis called a linear regression. We need to do what the computer calls a linear fit. How do we do that? Well, we go down to Graph Options, or Graph Tools, sorry, click on it, and here's a button called Apply Curve Fit. Click on that. And it gives us lots of choices, okay? We are going to most commonly use linear. And notice when it's linear, do you see it in there? It's drawing the best possible line of best fit. It's almost instantaneous. Watch this again. If I cancel this, if I go back in here and I choose Apply Curve Fit, right, it automatically puts a linear fit through there. If I hit Apply, it does something even better. Here, over here, right? Not only did it draw the line of best fit, but it gave me every stat I need to know, all right, about that line of best fit. It told me its slope. It told me its Y-intercept. It told me a number here that's known as the correlation coefficient. It's an R, okay? It's a little r is the symbol for it, but it's called the correlation coefficient. This is a statistical number that tells us how linear our data is. If your data was perfectly linear, if all these dots were right on top of the line, it would be a 1. So the closer we get to 1, the more linear the data is. Well, 0.9988 is pretty darn linear, right? So we could have a good deal of confidence that this was actually a linear graph. It wasn't some other shape. This last one we don't use in here. It's called a root mean square error. It's a different calculation, a different number that you're comparing to, so I don't worry about that one. Right? I mainly look at correlations for us in here. So it gives us everything we need to know about that line of best fit. Slope, y-intercept, correlation coefficient. And that's pretty much what we need to do with the graph at this point, right? So those are all of the things we can do here. Again, there is a sheet called Data Analysis with Graphical Analysis. Lives in a couple different places that you can find it, right? And it's something that I'll also give you, right? And it might be by your computer, right? But it's something we're going to use all year long when we're graphing. And it has all the steps to do all this and make everything look pretty and formatted and give us all the information we need to know. So I'm going to pop out of here and back into the PowerPoint. right? And here's something I copied and pasted earlier, right? You'll notice it's the exact same graph and all of the numbers. I made them a little bigger so that we could see them better, but here they are. Okay. And now the question is, well, what does that mean? Right? We've got this wonderful graph. We've got our line of best fit drawn through it. Right? We've got our linear fit, if you will. You'll notice that some of the points are above, some of the points are below, some of the points are pretty much on. It's taking an average of all of our data, if you will, giving us our best possible line. Well, what can we do with that? Well, we actually know how to make the math model of a linear graph, don't you? I mean, you spent a lot of time in Algebra 1 and Algebra 2 drawing equations for straight lines. And you even did, more fancy things, which we'll get to eventually, but we don't need for this lab. Right? You might remember a couple of different forms of straight lines. There's one right in the program here. Y equals mx plus b, right? And we're going to use that one in a minute. But before we do that, this is kind of special. Right? It's a linear graph, and it comes pretty close through going through 0, 0. We're going to talk a little bit about that, about why it doesn't and whether we can consider it 0. Okay, but in this case, the graph is pretty linear, and it goes through 0, 0. I mean, there wasn't even a 0, 0 data point. Well, what relationship does that represent? What does that tell us about what changing the time does to the height? Let's go back to our original numbers. So here's our, after 1 week, it was about 9.5 centimeters tall. Well, if we looked at it after 2 weeks, if we double the time, basically what happened to the height? It's not perfect, but it's pretty close to what? Twice, right? We double the time, we get roughly twice the height. Well, what happens if we triple the time? Yeah, it's about triple the height. If we multiply the time by 6, it's about 6 times the height. See how that's working? Right? Whatever we do to the time, we're doing the same thing to the height. Right? We double it, we get double. We quadruple it, we get 4 times as much. So this is a special kind of relationship when variables do that. Anybody remember what that's called? You've learned about it in math. You call that a proportionality, right? When variables change the same. This is a little different way of writing it than you wrote it in math class when you wrote it as like 2 ratios, all right, that were proportional to one another. The h here is a symbol that stands for height. Okay? I'm not going to use x and y because that's math, that's generic, right? I'm going to use symbols that mean something. So I'm going to call height capital H, and I'm going to call time lowercase t, just generic. This little symbol in the middle looks like an infinity sign with an open end on the right-hand side. This is called the proportionality sign. You would literally read this as the height is proportional to the time. Right? And again, that means if I double the time, it grows twice as much. If I triple the time, it grows 3 times as much. If I cut the time in half, I get half the height. Right? They are proportional to one another. This is one of several relationships we're going to see throughout the year, but it's kind of the basic one. Right? Not all things work this way in physics, unfortunately, but this one does. So now that we know the relationship, right, they're proportional to one another, we can write a math model for it by using our old friend y equals mx plus b. Now, I'm not going to use x and y, right, because I want to use symbols that are more meaningful to us. Otherwise, we'll end up with tons of equations that are all x's and y's, and what will that mean? Right? And I'm not going to use m and b. I'm going to use actual values we got out of the lab, which we got by doing our linear fit in the computer. So what might I use instead of a y? Well, y means what we graph on the vertical axis. We graph the height, so I might use capital H. M, of course, stands for slope. I've got a value for the slope. It's 9.954. But remember, we try not to draw or write naked numbers in here. We need context. We need units. Well, how do you find a slope? You find a slope by taking 2 points and doing rise over run. So that's how we're going to find our units. What are the units of rise? Well, the units of rise are the units of the vertical axis. So that's centimeters. What are the units of run? Well, those units, are the units of the horizontal axis, or weeks. So it's centimeters per week. But what does that mean? Right? And I don't mean from a math standpoint. That tells us every time we go up 9.954, we go over 1. Right? That's what it means in terms of like the steepness of the graph in math class. What does this physically tell us about how this pea plant is growing? Well, we're going to write a lot of meanings of slopes this year, and we're going to use what are called for every statements for that. All right, we're going to write a sentence in the form of for every this happens. Okay? So look at our units. Centimeters per week. All right, so this is what we're going to write. We're going to say for every week that goes by, what happens to the height? Well, the height of the pea plant grows by 9.954 centimeters. Okay? It's an average value. It's not that every week, right? But that's why we have the line of best fit. It averages out our data. For every week, the pea plant grows an average of 9.954 centimeters. And by the way, the week thing is because, this is a ratio. It's 1 week. It doesn't matter what our scale is. Look at our scale. Every line is worth a half a week. But when we define what it means, it's always this over 1, right? So it's this much growth for every 1 week. Okay? This is a for every statement. You're going to get a lot of practice with this. You're going to do a concept builder on it. And every time we do a lab, this is something we'll talk about. So this is the y equals m, all right, part of it. Well, what about the x? Well, x is what we graphed on the horizontal axis. We graphed time, not weeks. Weeks is what we measured it in. Time is what we were graphing. So a symbol for time, as we talked about, how about a lowercase t? Do you see how this equation has more meaning? And now we just have one thing, the y-intercept. Well, we could just throw this little number in here with the units of the y-axis, because it's a y-intercept, right? It's where it hits the y-axis. But we need to talk about this a little bit. Should it really be this number? What would that mean in this case? So we need some rules here to talk about the y-intercept and to decide whether or not it's significant. That means whether or not we're going to keep it. There's really two rules we're going to use here. The first one is the test of logic. Should the y-intercept be 0, 0? Or should it be something non-zero? And that basically means, what does it tell you? So think about what it would mean to have a 0, 0 point on the graph. Let's go back to the graph. This is a graph of height versus time. So what would 0, 0 on this graph mean? Well, it would mean when the time is 0, the height is 0. At 0 weeks, the height of the pea plant is 0 centimeters. Does that make logical sense? Well, we had a 0, 0 point in the data table, which meant when we planted the pea plant, it was probably just a seed, which has no height. So it makes logical sense that our y-intercept is 0. So from our logic is telling us that little number we got for a y-intercept was statistical error in our data. Okay? If we had instead, let's say we had planted a pea plant that was already grown, right? Then at 0 weeks, it might have had a height that was significant. And it would have made sense to not have 0, 0. We wouldn't have had that point in our data table. And we would have had a y-intercept that we would have added on. Okay? But in this case, logic is telling us we planted a seed, so at 0 weeks it should be 0 height. But I also want to talk statistics here. Now, we could do some complex statistics with error bars and standard deviations and some stuff like that, but I'm going to leave that for stats class and AP stats. I'm going to teach you a quick and dirty stats rule. This is not good stats. You will not see this in AP stats, okay? But it works for us in here. It's called the 5% rule. It works because we're controlling the labs and using a small range, and everything just kind of works well in here. It says that if that y-intercept that we got off our graph is less than 5% of whatever we graphed on the y value, the maximum y value, we can consider it to be negligible. Now, if you don't know that word, the root of it is neglect. So we can neglect the y-intercept. We can basically go, you know what? It's so close to 0, Let's just call it 0. Right? This is not great stats because it can be rigged depending on the range of your data. All right? But in my class, I'm not going to try to cheat you that way. So it works in here. Okay? But if you become an engineer, you're never going to use this. You're going to do some heavy-duty statistical analysis on it. But let's apply the 5% rule. Okay? It says take the maximum y value, which is the maximum height, which was in our data 60 centimeters. Take 5% of that. 5% of that is multiplying by 0.05 or dividing by 20, which gives us a value of 3 centimeters. So it says compare the y-intercept to that. Well, our y-intercept was a lot less than 5% of our maximum y value. So the rule says, you know what? This is so small because it's less than 5%, we're just going to call it 0. We're going to neglect it. All right, so think through that again here. We take the maximum y value, in this case the height, we find 5% of it, we compare that to our y-intercept. And by the way, this is positive or negative, doesn't really matter. It's on either side of 0. Okay? So if it's within 5% plus or minus, okay, if it's less than 5%, we just go and, you know what, it's 0. Especially if that matches the test of logic. Logic says we shouldn't have a y-intercept. Statistically, it's close enough. Let's just call it 0. Right? It's really hard to get a 0, y-intercept when you're taking real-life data, even if it's supposed to be. So this rule will allow us to interpret, right? But hopefully you're thinking, should it be 0? And then, does the 5% rule say it should be 0? Hopefully these things match. If they don't, you've got some issue going on, and that's when we're going to have to do a little deep thinking. But because in this case they both say, yeah, we can neglect it, we're just going to throw in a 0, and you don't have to add zeros, so there's our math model. So we have gone from taking data in a data table to putting it into a graph so that we get a picture of it, and with that graph we can figure out the relationship, which happened to be a direct proportion in this case because it was a linear graph that went through 0. We then created from that graph a math model, which we converted the x and the y to actual variables that are meaningful, to symbols that are meaningful, and we plugged in numbers that we got out of our linear fit, right? Our slope, which we can explain what it means, and our y-intercept, which we decided was 0, right? And we built this math model. But once we have the math model, the beauty of this is that it allows us to make predictions. We can now put in any time we want. How tall do we think it was after a week and a half? Plug in a week and a half and multiply, and you get the height, right? That'll be a kind of an average value. We can go the other way, right? If we want to know how long should we grow it so that it'll be 20 centimeters tall, we plug in 20 centimeters, do a little algebra, it'll tell us a time. Right? The math model is a super powerful tool that allows us to make predictions about what's happening in nature. It's not just math, right? It's modeling reality. This is the kind of thing we do when we do labs in here. So our next step when we're back in class is that we are going to actually do this with your data from the Circle Lab. Right? We're going to create a math model, a graph, and then a math model out of our linear fit, right, for our data, our Circle Lab data. And then we're going to talk about what that all tells us about circles and look at our math model, right, for it. So I hope you enjoyed this kind of in-depth thing about how we are going to use graphical analysis to make graphs and then turn those graphs into math models.